let's go over the first problem from this contest, which is Cowdependence. So for this problem, we have Farmer John's and cows arranged into a line, and each cow has some label A of I. And then what we need to do is we need to output for every single value of X, the minimum number of groups it takes, such that every cow is in exactly one friend group. And cows of the same ID have to be like friends with each other. Okay. So for this problem, let's start with a O of n squared solution. So given a fixed value of X, so let's just say we set X to be 2 here, we can just go through the whole entire array and greedily assign the groups, right? So whenever you get a new ID, you have to put that cow into a group. So for this one, we have to put it in a group. So therefore, we'll start 1 here. And then for this one, we see that, oh, there's already a group that was started at index 0. So they can just go in that same group. And the same thing with this one. It can also go in that group. And then we get another +1 at this 9. Another +1 at this 2. So we have to start a new group. For this one, we check the previous one group, and it's too far away. So we just add another one. Maybe let's start this. And then similarly, this 2 does not need a new group. This 1 does not need a new group. And finally, this 1 does. So that's how we get that for X equals 2. You get an answer of 5. Right. And so if we just run this for every single value of X from like 1 to n, our overall runtime is n squared. Okay, so now let's look at the subtasks. And it turns out the subtasks here are kind of telling for what you need to do for this problem. So the first thing is, what if we only had up to 10 unique IDs, right? So essentially we have a bunch of like big groups of cows, and there's only 10 distinct IDs. We just need to figure out how to group some, like a few big groups. And then for our next subtask, no like ID is repeated more than 10 times. So basically we're gonna have a lot of small groups of cows, and we also need some algorithm to figure that out. And then the idea is probably along the lines of, if we figure out both of these subtasks, maybe we can just merge the two solutions for the full problems. Yeah, for the full solution. Okay, so let's start with the case where A of I is less than or equal to 10. Okay, so let's go ahead and use B to denote the number of group, or B to denote the size of your groups. So in this case, B is roughly, or it's like at least n over 10, okay, so most of your groups are going to be quite large. So just say, yeah, B is really large. Okay, so how do we solve like for a big group the answer? Well, one thing is we can actually just brute force each group on its own. So let's say in this case we have a bunch of 1s, right? Let's just go ahead and get the indices of all the 1s. So we have a 1 at index 0, 1 at 2, or 0, 1, 2, and then. Okay, so these are the indices of all of our 1s. And if we just store this in like a set or a vector and sort this, then we can easily simulate the number of groups needed just for this ID, right? So let's start with X equals 1. What you can do is you can just start at the first cow, make it a group, and then you can use binary search or like upper bound, lower bound to find the next place you need to start a group. So you start a group here, then this can cover everything in the range 0 to 1. So you next need to start a group at 2, right? Okay, so you start another group here, and then you start another group, and that's it, right? So this would be 4 for X equals 1. And then you can do this for X equals 2, and so on and so forth. And the key thing to note is that as X is increasing, the runtime of our algorithm gets much faster. So in the worst case, let's just assume you had every single index in your group. Then what happens is when you have X equals 1, if B is the size, it takes us around B over 2 iterations, right? Because you can only group them into like groups of 2. And then when X is equal to 2, you get like B over 3 iterations needed. Because this would be the first group, this would be the second group, so on and so forth, right? Okay, and so essentially what we have is we can analyze our runtime using harmonic series here. Because effectively we have like, b over 1 plus b over 2 plus b over 3, so on and so forth. All the way up to like b over n. Okay. And, or I guess let's just analyze this in terms of n. So assume you're like, you just have one big group. Okay. And this would just be n log n in terms of the number of like binary searches we need to do throughout this whole sequence. Okay, so we figured out that our runtime is at most like n log n or n log squared n if you had exactly one group. So if you have only like 10 groups, then what we can do is we can just do 10 times like n log n or n log squared n, and that gives us our solution. So essentially for our first subtask, all we need to do is simulate each group individually, and that's going to be fast enough as long as you use this jumping method or binary searching to jump to the next group. Okay. So next, let's take a look at our subtasks when the size of our groups are really small, right? So each label appears at most 10 times. All right. So the idea here is now, let's say we have like a few positions. So like 0, like 5, like 30, and like 100. So let's say these are the indices where like ones appear, right? And we want to figure out what the answer is for each value of x from 1 to n. So it'd be very, very wasteful to just like simulate the process for each value of x, because one thing we can note is that the answer doesn't change that often. As an example, if you pick x equals 1, your answer is going to be 4, because each cow will be in their own group. But even if you pick x equals 2 and 3, your answer is still 4, because every cow still needs to be in the same group. So what we can do is we can just figure out, well, let's just figure out for every single answer, what range of x gives you that answer. Okay, so let's write it out here. So for our example here, if you want an answer of 4, right, then your range of x can be anywhere from 1 to 4. Yeah, because if you pick 1, or even if you pick up to 4, every cow is going to be in their own group. Okay, what if you want your answer to be 3? Well, then the minimum value of x you have to pick is going to be 5, because if you pick 5, then the first 2 cows will be put in the same group. And so this answer will only be 3. And now it turns out we can actually go up quite large, up to 29, and still get an answer of 3. Right. Okay, and then similarly, we can do the same analysis for, well, when will the answer be 2? And in this case, yeah, so you start from 30, and you can go all the way up to 99. Because, yeah, so if you pick 30, this will be in one group, this will be in a second group. Even if you pick 99, that's still the case, right? Now, finally, if you want to answer 1, you need to pick at least 100. And then it doesn't matter where your upper bound is, so let's just say up to n, right? So we can figure out the ranges in which, or like the ranges of x for every single answer. And the thing is, because there's not that many elements within each group, like this is going to be bounded to 10, right? So if we can just figure out all the ranges for each of these 10 possible answers, then we can pretty quickly compute the answer. And then just one last note about how to actually compute this, like to output the final array. What you can do is once you have all these ranges, you can think of this as you just want to add like 4 to this range of x, add 3 to this range of x, add 2 to this range of x, and add 1 to this range of x. And you do this for every single group. And so you can use like any data structure you want, but one way is to just do a difference array, because we're just statically adding some like range, and then we care about what the array looks like at the very end. Okay. Yeah, so that's how we can get our 8 through 11 test cases, where everything only appears 10 times. Oh, sorry, one quick note about how to actually get these ranges. What you can do is you can just binary search for the range in which the answer is 4. Yeah, so basically, if our target is 4, we can binary search on value of x from 1 to n. Let's say first we tried 50. We can just evaluate what the answer would be with x equals 50, and we see, oh, it's 2. So if our answer right now for 50 is 2, and we're trying to get the answer to be 4, we know we have to decrease the value of x to try to get to 4. So next we can maybe try 25. And we see, okay, 25 is a 3, so we have to go even lower. Maybe we try 12. 12 is still a 3. Then we try 6. 6 is still a 3. And then we can try 3. 3 is now a 4. But what you want to be able to find is the lower and upper bound of this. So there's a few ways you can do this. You can either run like 2 binary searches, one to find the higher end, one to find the lower end. The other thing you can do is you can go backwards. So we know that for the answer of 1 valid answer is definitely n, right? So if you set your answer, or if you set your value of x to be n, you're definitely going to have 1 as your answer. So then you can just binary search for the lower bound of what 1 would be. And we find that it's 100 in this case. Now this automatically gives us the upper bound of our next answer. So we know since 100 is the lower bound for 1, we know that the upper bound for our next range is at 99. Yeah, so then we get this 99 for free, and then we just have to binary search for the lower bound of that range, which is 30 in this case. And then again, we get 29 for free, and then we binary search for this 5, and so on and so forth. Okay, and yeah, another note is that these answers might, like for every single possible answer, there might not exist a range. Let's see, as an example, okay, so here's a simple example. Let's say you have like a 1 at position 2, another 1 at position 3, and another 1 at position 5. The answer of 3 doesn't exist because the lowest you can go is 1. And even if you use 1 as x, you still get only 2 groups, right? So that's a simple example where like the answer being 3 doesn't exist, but this could happen for any of the numbers in the range from 1 to like size. Okay. Cool. So next, let's go over how we can combine these two solutions. So there's a few ways you can do this. The most typical square root like decomposition idea is let's just set some threshold b to be square root of n roughly. And if your group is larger than b, so basically if you have some ID and there's more than square root n occurrences of that ID, we can just use the algorithm we used for our inputs 4, 3, 7. And if the number of elements is small, aka less than b, then we can just use the algorithm we used for when it's small. Okay, and let's quickly analyze the runtime for why this actually runs in time. So first of all, if your group is big, we know that the worst case runtime of a given group is n log n, or n log squared n. This is assuming the biggest group you can possibly have, which is like a group of size n. Okay, and the maximum number of big groups you can have is at most square root n. Because each of our big groups is, or let's just use B here. Because each of our big groups has at least square root n numbers, so we can have at most square root n big groups. So the total runtime of our big groups is at most n square root n log squared n. Okay, now let's also analyze our small groups. So for our small groups, we're also going to do an upper bound runtime here. So to do each singular small group, the runtime is b squared log n. Because we're going to binary search on each answer from 1 to b. And then so that's how many binary searches we're running. And for each binary search, of course, there's log n iterations. And to complete each run, our worst case runtime is b log n. It's actually quite a bit smaller than this, but worst case is like you go through the elements one by one, and each time you're doing binary search, so it's b log n. Okay, and so if you go ahead and multiply this by the number of groups you can have of the small group, it's n over b, where b is like the size of your small groups. And then, so this can cancel out. And we get n times b times log square root of n. And then finally, b here we set to b square root of n. So this is our upper bound for our small group runtime, and this is the upper bound for our big group runtime. Yeah, so this would be our overall runtime. And this is a very rough upper bound. I think with some more careful analysis, you can find that it's actually faster than this. But regardless, this is like good enough for 10 to the 5, especially knowing that the constant factor is really good and that this runtime is done assuming you could, like for some given value of x, you had to loop through all the elements one by one, which we know is not the case, especially for larger values of x. And then an alternative solution, so this works, and the alternative idea is we can actually just not worry about the big small group thing, and we only run the small group algorithm. Now, the problem with the small group algorithm is that if you have like a really big group, and you're binary searching over all the possible answers, so when you binary search for all the possible answers 1 through n, what's going to happen is you're going to repeatedly run the calculation for a given value of x. So yeah, so for example, when you start your binary search on, okay, when is the answer 1? You first computed it for x equals n over 2, and then you went either down or up, and so on and so forth. And then when you do this for when the answer is equal to 2, you're going to do the same thing, right? You recompute what it is at n over 2, then you might go smaller or larger, but then you probably also recomputed that one, and so on and so forth. So what we can do is if you just cache all the results, so basically for any given value of x, if you've computed it before, just don't compute it again. So it's sort of like a memoization DP idea. Then this guarantees that what's going to happen is you have exactly n log n calls on your like evaluate function. And each position of the, like for every single given value of x within a group, it can only be evaluated once. So then we still have the nice harmonic series runtime analysis to keep our runtime manageable. And in that case, the runtime, it's still hard to upper bound, but the runtime is quite good. And the upper bound is definitely going to be O of n square root n times log square root of n. Yeah, so this is still the rough upper bound. But if you actually implement this and submit it on USACO, the maximum test case was only like 500 or 600 milliseconds. This passes very comfortably. Okay. Yeah, so that's it for this problem. Overall,